In case of electrostatics, we have defined the electric scalar potential as the potential energy per unit charge. So in the same manner, we can define the magnetic potentials as potential energy per unit current. So here in this video, we'll discuss two types of magnetic potentials: magnetic scalar potential and magnetic vector potential. So we'll discuss here the related equations and the significance of these potentials. Let us proceed. So magnetic fields are related to these two types of potentials: magnetic scalar potential and magnetic vector potential. The unit of magnetic scalar potential, it is ampere, whereas the unit of magnetic vector potential, it is Weber per meter. So first we will discuss about the magnetic scalar potential. Now in case of electrostatics, we have seen this equation E equal to negative gradient of V. So this equation gives us the relationship between the electric field intensity and the electric scalar potential V. So similar to this expression, do we have the relationship between H and the scalar magnetic potential? So this relationship is exactly similar to E equal to negative gradient of V. So in case of magnetic scalar potential, we write the similar equation as H equal to negative gradient Vm, where Vm is the scalar magnetic potential. Now, as we have defined the relationship between magnetic field intensity H and the scalar magnetic potential as H equal to negative gradient of Vm, where Vm is the scalar magnetic potential. So for any scalar quantity, it must satisfy the equation curl of gradient of Vm is equal to 0. We will substitute for this del Vm as minus H. So substituting del Vm as minus H here, this gives me del cross minus H is equal to 0, or del cross H is equal to 0. That is, curl of H is equal to 0. But we have seen one of the Maxwell equations that the curl of H is equal to current density. So these two equations are contradictory. One equation says curl of H is equal to 0. From Maxwell equations, this equation says curl of H is equal to J. Both these equations are satisfied only if current density is 0. So the scalar magnetic potential is defined for J equal to 0. That is, current density is equal to 0. So this equation H is equal to negative gradient of Vm is true only if J is equal to 0. So that is the conclusion from this discussion. Now in case of electrostatics, we find out the scalar electric potential V in terms of electric field intensity by using the integral V is equal to negative integral B to A E dot dl. So this equation gives us the scalar electric potential from electric field intensity. So in the same manner, we can write the expression for scalar magnetic potential as VMAB equal to negative integral B to A H dot dl. So for a specified path B to A, this expression we can use to find out the scalar magnetic potential having knowledge of magnetic field intensity. So this is what is scalar magnetic potential. Now in case of electrostatics, we have seen the Laplace's equation for electric scalar potential. So in the similar lines, we can find out the Laplace's equation for scalar magnetic potential. So to begin, let us consider this equation. Surface integral B dot ds is equal to 0. So this equation we have written earlier, assuming that magnetic flux exists in the form of loops. So if I consider some area, the flux entering inside this closed surface is equal to the flux leaving this closed surface. So based on this, we have written this equation earlier as surface integral B dot ds is equal to 0. Or in other words, the single magnetic pole does not exist. So that is the significance of this equation. Now using divergence theorem, we can convert this surface integral into volume integral. So integral B dot ds equal to volume integral divergence of B dV equal to 0. Now dV is a differential volume which is not equal to 0. So if dV is not equal to 0, so that means del dot B, it must be 0. That is, divergence of B is equal to 0. Now for this B, we substitute as mu 0 H. We know mu 0, it is a constant, that is the permeability, and which is a non-zero quantity. So from this we can conclude that divergence of H must be 0. Del dot H is 0. Now using the relationship between H and scalar magnetic potential, we substitute this H as minus del Vm here. So this is the del dot minus del Vm is equal to 0. So this equation we can simplify as del square Vm is equal to 0. So this is the Laplacian equation for scalar magnetic potential, which is similar to Laplace's equation for scalar electric potential, which we have studied in electrostatics. So the Laplace's equation for scalar magnetic potential, which we have defined just now as del square Vm is equal to 0, this is true only if current density is assumed to be 0. So this is about the Laplace's equation for scalar magnetic potential. Now let us discuss about what is vector magnetic potential. So if we denote this vector magnetic potential by a symbol vector A, then using the standard identity for any vector, divergence of curl of that vector, it must be 0. So that means del dot del cross A, it is equal to 0. But just now we have seen divergence of B is equal to 0. So if I compare these two equations, then I can write B as del cross A. So using this equation, we can define the vector magnetic potential based on the magnetic flux density B. So this equation gives us the relationship between magnetic flux density B and vector magnetic potential A. Now from Maxwell's equations, we know del cross H is equal to J. That is the current density. So substituting for H as B upon mu 0, we can express this equation in terms of B. So this gives us del cross B equal to mu 0 J. Now, taking curl of this equation on both sides, this gives me del cross B, that is curl of B, as del cross A. Now del cross B is nothing but mu 0 J. So for this del cross B, we can substitute this del cross A here. So we can write this equation in terms of vector magnetic potential. So which will give us the relationship between vector magnetic potential and J. That is the current density from this equation. Now we have a standard mathematical identity as del cross A is equal to del dot A minus del square A. So this is true for any vector A. So substituting this right hand side here. Now rearranging these two equations, we can express J in terms of the vector magnetic potential A. So this equation gives us the relationship between the current density J and vector magnetic potential A. In electromagnetics, the main application of this concept of vector magnetic potential is to find out the potential induced in the antenna. For example, if we have a transmitting antenna here, now in this antenna, suppose the current density, some current is flowing through this antenna, and at other place there is a receiving antenna. Now if you want to find out what is the potential induced inside this antenna, so that potential is the vector magnetic potential A. So using this relationship between J and A, we can find out the potential induced inside the antenna. So that is one of the main application of this concept, vector magnetic potential. Now as we have seen earlier, for scalar magnetic potential, the current density is 0. Whereas vector magnetic potential we can define when J is not equal to 0. There exists some current density. So because of this, we can now define Poisson's equation for magnetic field. Now in general, any vector can be defined if its curl and divergence are defined. So for vector A, which is vector magnetic potential, as we have seen earlier, curl of A is the magnetic flux density B. So that means curl is already defined. Now to define divergence, let us assume divergence of A is equal to 0. So this way we define curl as well as divergence for this vector A. Now using the expression which just now we have derived, which gives us the relationship between the current density J and A as 1 upon mu0 curl of A equal to 1 upon mu0 del dot A minus del square A. Now, as we have assumed, del dot A is equal to 0. So, if I substitute this del dot A equal to 0, then the equation for current density we can simplify as J equal to 1 upon mu 0 minus del square A. So, rearranging this equation, this gives us del square A equal to minus mu 0 J. So, this is nothing but the Poisson's equation for magnetic field. In the same way what we have defined Poisson's equation for in case of electrostatics. Now, from the equations what we have written earlier, these equations give us the relationship between J and A. So that is the relation between the current density and A. Now, we can have different types of current elements like line current, surface current, or volume current elements. So, if it is a line current element as IDL, then because of this line current element IDL, the corresponding vector magnetic potential developed at the antenna can be determined using this equation. So that is E equal to integral mu 0 IDL upon 4 pi r. So as we have seen earlier, the unit of vector magnetic potential is Weber per meter. So in the same manner, if this current element is a sheet of current KdS, the current flowing through this sheet of current, K is the current density in ampere per meter. In this case, the vector magnetic potential is given as mu 0 surface integral mu 0 K ds upon 4 pi r Weber per meter, where r is the distance between this current element and the point at which we are going to determine, we are going to find out this potential A. So in the same manner, if it is the volume current element dV, in this case J is the current density in ampere per meter square. So the vector magnetic potential, because of volume current element, it is volume integral mu 0 I dV upon 4 pi r Weber per meter. So these are the vector magnetic potentials because of the line current element, surface current element, and volume current element. Now we will solve one example to clear our concepts. So the problem is the vector magnetic potential A due to a direct current in a conductor in free space is given by A equal to x square plus y square Az Weber per meter. Determine the magnetic field produced by the current element at point 1, 2, 3. So here A is given, that is the vector magnetic potential is given as x square plus y square, which is oriented in z direction. So that is Az, microweber per meter. Now from this we have to find out the magnetic field intensity produced by the current element. So let us proceed. Now we have defined the vector magnetic potential as B equal to del cross E. Now in this problem, A is given, the vector magnetic potential is given as x square plus y square. Now from A, using this equation B equal to del cross A, we'll find out B, and from B we'll find out H. So let us write the equation for del cross A. So this equation B equal to del cross A, Cartesian coordinate system. So we will have unit vectors as Ax, Ay, and Az. So d dx, d dy, and d dz. This vector magnetic potential, it has only z component. So x square plus y square, and it has only z component. So x component 0, y component is 0. So there is only z component. So that we write as x square plus y square. And this is given as microweber per meter. So we take it outside as 10 raised to minus 6. So expanding this, z component is Az, it will be 0 because ddx 0, 0, ddy 0, 0. Only x, there will be only x component and y component. So x component, now this is dy x square y plus y square minus ddz into 0. So that is 0. So this is x component plus for Ay, this is minus ddx x square plus y square Ay into 10 raised to minus 6. Now solving this gives me x square plus 2y ax minus 2x plus y square ay into 10 raised to minus 6. So this is B, that is the magnetic flux density. Now in the problem it is given that determine the magnetic flux density at point 1, 2, 3. So let us substitute x equal to 1, y equal to 2, and z equal to 3 here. We get B as x equal to 1. So this is 1 plus 2 into 2, that is 4 ax, minus x is equal to 1. So this is 2 plus y is 2, so 2 square, this is 4 ay into 10 raised to minus 6. So solving this, this is 5 ax minus 6 ay into 10 raised to minus 6. Now from b we can find out h as 1 upon mu 0, 5 ax minus 6 ay into 10 raised to minus 6. Now substituting value of mu 0 here as 4 pi into 10 raised to minus 7. So this is 4 pi into 10 raised to minus 7. So this is 5 ax minus 6 ay into 10 raised to minus 6. So solving this, this gives us h equal to 3.978 ax minus 4.774 ay ampere per meter. So we have determined here the magnetic field intensity from vector magnetic potential. So in this video we have learned the concepts and the equations about the scalar magnetic potential and vector magnetic potential.